I'm Simon Sturgess. My company, Sturgis Carbon Profiling, is first of all, I'm going to talk to you about, as I said, the professional statement. Now, of course, why on earth are we doing this in the first place? And I think the really key point is we're trying to solve two major problems. One is a direct consequence of carbon emissions, which is global warming, and the other one, which is resource depletion, is, if you like, a less direct, but it is, if you like, in parallel to carbon emissions. And certainly the two things seem to work together. And so really what we're saying is that if you can do better on carbon emissions reduction, you will also be doing better on resource depletion. The other key issue is the relative impacts of embodied and operational emissions. Now, in this diagram, these three diagrams here, you're looking at pie charts which show in grey the operational energy costs, the dark grey, over a 60-year period, and the calculations in this pie chart are done at design stage and allow for grid decarbonisation. So the dark grey represents your Part L costs over the 60-year period. The light grey represents the other costs, which are things like, so the dark grey is heating, lighting, cooling. This will be small power, kettles, photocopiers, TVs, all that kind of thing, lifts, and so on. And the dark purple represents the construction emissions. So that's what it takes to build a building. And the lighter purple is the replacement costs of components and systems over the life of the building. Now, if you look back a couple of years, people like the Green Construction Board were suggesting that the purple bit, instead of representing, as you can see here, in excess of 50%, was represented about 20% of the total energy cost. The reason for this discrepancy is primarily because in calculating the embodied carbon, what people were doing is only focusing on partial assessments. So they were looking at, say, just the structure and cladding, but not including things like the interiors, the MEP, and so on. And of course, if you don't include those at the beginning, and then you also don't include the replacements, you're making a big error of statistical error, which I'll come to, as you will see later. So the next issue is to do really with the relationship between operational and embodied, and it's a kind of cost-benefit thing in terms of emissions. So if you're looking at, and this is the World Wildlife Headquarters that we worked on some years ago, and the question came up was, should this be double or triple glazed? And these are these big, huge sheets of glass. I'll just make a key point that what I'm about to say does not relate to all triple glazing, it's just in this particular case. So the benefit of the third sheet of glass over 60 years was about 11,000 kilograms of CO2. But the cost, and so therefore, based on that assessment, you definitely go for the triple glazing. But if you looked at the cost of that triple glazing, and in both cases, whether it's double or triple, we assumed it would be replaced about 40, 50 years in. The actual cost of that third sheet and the framing was about 13,000 kilograms. So in that instance, really what you should be looking at is the double glazing, and in fact that was what was installed. So whilst it is absolutely correct to say that in operational terms the triple performs better, it wasn't sufficiently, or by a sufficient margin, to overcome the embodied cost. Another issue which James already mentioned was the lack of consistency in the way people are doing carbon assessments. So, as he said, you had 3 different people doing 3 different assessments. You get apples, pears, and oranges. So the idea was to make it more consistent. The other one was to enable the broadest take-up and to get industry, make it as accessible as possible so that people right across industry would actually engage with carbon assessments. Now this is the team that worked on it, and we led it, and Athena Papacosta and myself were the co-authors after a year and a half process where we worked with Arups, Atkins Faithful and Gould Sustainable Business Partnership, Lang O'Rourke, Landsec, in fact Ed Dixon, team member, is going to speak a bit later, Cambridge University, RICS, and the UK Green Building Council, and not last but by no means least was Innovate UK, who funded it all. Now, as James mentioned, we had the consultants did 5 different assessments. Cambridge University then processed all that, and we worked out where all the gaps were, where the inconsistencies were, and we spent about 9 months going through all that, and then we wrote the document. After that process, the initial draft of the document, the group on the right, the expert panel, including Jane Anderson, who's over here in a wheelchair, were critiqued what we'd done, and we made quite a few significant changes of principle of how the document should be used, and then it went to be launched. So, taking you through the document, I'm going to take you through sort of the five sort of key areas. The first one is determining the object of the assessment, then carbon data sources, factors influencing the assessment, the life cycle stages, and finally reporting requirements. So coming with the first bit, determining the object of the assessment. And the first bit of this is the spatial boundaries. And this is pretty straightforward in a way. I mean, typically you might use a planning red line. And again, I'm really paraphrasing. There's a lot more detail on each of these issues, of course, in the document. But you might use a planning red line or a property boundary, and indeed the scope of a cost plan. In terms of the built asset physical characteristics, this is based on the standard BCIS, the RICS classification. So you've got things like demolition, facilitating work, substructure, superstructure, frame, superstructure cladding, superstructure, internal walls, and so on. And you've got various other bits there. So that is all based on the standard RICS methodology for collecting information on buildings. Then we've got the reference study period. And this is relatively simple. For domestic and non-domestic, 60 years, and for infrastructure, 100 years. So that is the period over which the assessments are done. Obviously, buildings might be designed to last shorter or indeed longer than that, and the document explains how you deal with those issues. But the reason for these periods is it's a reasonable time frame to include changes in things like cladding and plant, but it's not so far into the future to make life impossible to sort of a guesstimate, if you like, but also gives consistency. And again, that's the other thing that we're trying to achieve here. So floor area and quantities measurement is also based on RICS documentation. This is the RICS property measurement, IPMS, and the BCIS elemental standard form of cost analysis. So all of that is the basic tools, if you like, of floor area and quantities. Units of measurement, most of it would be in kilograms of CO2 or equivalent per square meter. For something like sheds, it could easily be cubic meter. And for things like infrastructure, railways, it might be by per kilometer or per kilowatt hour or per passenger and so on. The main thing is that as long as you do it consistently, if you're trying to compare things, you obviously want to have a consistency of how you're using which units you're measuring things in. Carbon data sources. This is obviously one of the more sort of difficult bits, and it is a constantly moving target. Now, what we've tried to do with this is to start off by saying that it's basically a hierarchy we've got here. So this is straight out of the document, this purple patch of text, and the primary source of information would be EPDs, environmental product declarations, consistent with EN 15804. But if that's not possible, then it's EPDs consistent with ISO 21930, and it goes on here with alternatives. I think it's fair to say that because things are moving, and as I said, the data is being collected, not least by the RAP database will start. This will get better. Obviously, it's not perfect at the moment, but this is the beginning of a journey, I think, and at least what we're trying to do here is identify the sort of standards and sourcing of information that will start to bring consistency. Carbon sequestration, this is to do with factors influencing the assessment. So carbon sequestration is one, how you deal with timber, biogenic carbon, and how that needs to be calculated. And of course, there are two crucial features of this. One is the sourcing of the timber. It's absolutely vital that it's sustainably sourced. The other one is what happens to it. And you can't consider timber without thinking about what its disposal is, because how it is disposed can have a huge impact on the carbon cost of something. And in fact, if you don't use timber intelligently and well, and for example, the things like glulam or CLT, if you don't use good, sensible glues, timber can actually be a problematic material in carbon terms. So it's not an easy win. You've got to think it through. The one at the end there is carbonation, which is new concrete, raw concrete will absorb CO2, or indeed if you demolish a concrete structure, leave it for about a week or so, it will also absorb CO2, and that can be assessed. The other factor influencing the assessment is future energy projections, and what we've called for in the document is the slow progression, which is this purple line, which is a kind of intermediate position. Now, what the document does is it actually, as we've said, we're trying to be consistent with EN 15978. But EN 15978 does not allow for grid decarbonisation at this point in time. So what we've asked for is that you basically do two things. One is do it in accordance with EN 15978, i.e. you do not include grid decarbonisation. But because the government's policy is to have the purple line, we've said you should also do the purple line. So that, because to me that makes kind of sense in terms of what the trajectory across the next few years will be. So this is what the EN 15978, you can't really see this, but what you're looking at is a series of modules, and I'm going to show you this one, which is a sort of simplified and more colorful version of the previous document. And I'm going to use this to talk you through the stages. So the product stage is modules A1, A2, A3, and this takes you through raw material supply, transporting of material, and manufacturing. And I think what is really of importance in something like this is that, and to give you an example of why these sorts of things are important and where the raw material comes from, because of course raw material could also be recycled material. And if you think about choosing cladding, for example, and you're using, let's say, aluminium, and this is a bauxite mine in Australia, if you're choosing aluminium, for an architect or the person specifying it, whether it's powder coated or anodized may seem like a purely an issue of color. But if you're anodizing aluminium, you need the raw aluminium to be absolutely consistent in color, which means it needs to really come from somewhere like this. If, on the other hand, you're powder coating the aluminium, it means that it can actually be recycled content, because if there's slight variations in the color of the aluminium, it doesn't matter because the powder coating will deal with that. So what is seemingly like a simple choice actually has big ramifications in terms of procurement, the supply chain, and the carbon cost in terms of whether it comes from here or recycled material and so on. The next bit is the construction stage. Again, transport and site works, and that takes you up to practical completion when the project is now finished. And then we move into the in-use stage, and the first bits of this are to do with things like maintenance, repair, replacement, and refurbishment. So this scheme here you're looking at is a building that's 35 years old and was reclad after that period. And you think, well, is that really a sensible use of resources? Should we be needing to reclad these buildings after such a, that's the sort of turnover. As it happens, this scheme of recladding was done by my architectural practice several years ago. And now when I step back and look at it, I realize, well, this is not going to last a hell of a long time either. This is going to be something that's going to need to be replaced. I hope there's nobody from the client here, but it's not this is not a long-term solution. You think, well, is that really a good way to be proceeding? Central plant and fan coils and lifts and so on, these things get replaced on a 15, 20, 25-year cycle. And all of these things have a significant carbon cost to manufacture and ultimately dispose of. And then, of course, there's the sort of regular fit-out and so on that happens over the course of the life of a building. We then have operational energy use and operational water use. And for the calculation, the operational energy use is really all the things you would imagine. The operational water use, what this is including is the carbon costs of moving water around, storing it, and disposing of it, and so on. This bit, the end of life stage, is to do with demolition, disposal, and preparing things for waste processing, transport, and so on. And this really takes you to what you will have heard of as sort of cradle to grave. The last bit, reuse, recovery, and recycling, is treated as a sort of separate calculation, and it's to do with scenarios looking to the future. So if all of this represents your cradle to grave and your whole life, your sort of standard whole life equation, the reuse, recovery, recycling is to do with more to do with the circular economy. This is the Sterling Prize winner, the Hastings Pier, and all of this timber here is from the old pier decking and is now being used here. And of course, all of this is an old pier that's been recycled. So the whole thing is a recycled building. The new decking is, the timber's reputed to last 100 years. I can't remember what it is. It Ecoya? It's a really hard timber. This diagram here is basically the same report, but this is the reporting template. So you've got the same modules across here. So you've got module A, module B, module C, and module D. And as you can see, D is separated out. So these are the basic modules you use to report cradle to grave. And then we've got the building element categories. And again, this is according to that, as I showed you earlier, the BCIS. So we've got demolition, facility work, substructure, superstructure, finishes, and so on. And then we have the minimum reporting requirements. So in an ideal world, we would ask everybody to do everything. But one of the things that came out of the consultation with the expert panel was that that would probably put anybody off doing anything. So we have a sort of minimum requirement, and the minimum requirement is for the substructure, the superstructure, that's the frame, upper floors, roof, stairs and ramps, superstructure, external walls, windows and external doors. So that is the sort of basic up to practical completion assessment. But in addition, we've of course got, already you have the lifetime assessment of the carbon emissions from in use, so that is the operational emissions. And what we've got here is the cladding. You look at the life cycle of the cladding. So what this is asking is that the architect considers the life cycle of the cladding from the point of view of designing. What happens to it, how it gets disposed of, can it be dismantled, and so on. But also the relationship between these two things is very important. And as I was showing you in that earlier slide about the WWF glazing, the idea really is to encourage people to really think about the long-term interrelationship between these two things, the cladding and the overall building performance. The next stage up is cradle to grave, as I mentioned, and that would be really a kind of an ideal. And if you're really enthusiastic, you'd be doing the full whole life, which would include module D and demolition. This extra bit along here is demolition. And the reason demolition is separated out is because, of course, you can have two identical buildings, new buildings. If you're demolishing a lot on one site but nothing on the other site, you're going to skew the whole statistic. So the idea is that you're focusing on the new build, but you're accounting for this. Another point I want to make about this is that the way the document is structured is to do with, if you like, musts and shoulds. So and this is to do with carbon data sources again. So this says the assessor must explicitly state, etc., and that therefore is your sort of requirement in terms of the mandatory aspect of it. The shoulds, so type 3 environmental declarations should be issued, blah, blah, blah. The shoulds are really to do with best practice. And I think, unless I'll get this wrong, James, I'm sure will interject, but this is to do with the mandatory bit, this is best practice, and it's structured in that form, which is a standard RICS professional statement structure. Also, at the end of this, we have an indicative step-by-step guidance to how to undertake a whole life carbon assessment. So the benefits, therefore, are, we're hoping that will become clear as people use this, are the consistent and transparent reporting of all the carbon emissions to do with the building, the comparability of assessments, that's really important to enable people to compare like for like, building for building, improve take-up and accessibility, encourage people to undertake carbon assessments, develop a solid source of reference for the industry. James mentioned the RAP database. Promote long-term post-practical completion thinking. I think this is really important, is that when you're designing a building, you really do think about it not just as let's get it finished and we'll move on to the next project, but really what happens to those buildings over the life of the building. Promote, same sort of principle, promote circular economic principles, enable benchmarking and target setting, and through life cycle analysis respond to climate change. So you can, if you're obviously doing a life cycle analysis right across all this, you can connect into climate change. And finally, back to the beginning, reduce carbon emissions and improve resource efficiency.